professeur Frédéric Dupont-Dupuis, qui est professeur au département d'informatique et de recherche opérationnelle, le DIRO. Donc, professeur Dupont-Dupuis est un spécialiste de l'informatique quantique théorique. Puis présentement, corrige-moi Frédéric, professeur adjoint sur le site web, c'est ça qui est. Donc, t'étais où avant, Frédéric? J'ai pas trouvé sur le Internet.
Oui, j'étais au CNRS à Nancy, en France.
Super. Donc, Frédéric nous arrive de la France, malgré qu'il est né au Québec, on s'en doute. Puis donc, c'est ça, on a hâte d'entendre ce que tu vas nous dire. Puis on l'espère peut-être entamer une discussion là, qui va durer au fil des années. Donc, Frédéric va nous parler de... Well, so first I can switch to English. So Frédéric will give his seminar in English. So if you don't speak French, do not run away. But I think you can ask questions in French because French is okay. It's not great, but it's fine. He will talk today about quantum cryptography with untrusted devices. So Frédéric, we're all yours for the next hour.
Okay, well, first of all, thanks a lot for the invitation. It's a pleasure to give a talk here. And I'd also like to start by giving my condolences to friends and families of the deceased. So yeah, I'm going to be talking about quantum cryptography with untrusted devices, and this is some work I did a few years ago with these people here. So Rotem Arnon Friedman, Omar Fauzi, Renato Renner, and Thomas Wittig. So here's a brief outline of what I'm going to talk about. So I'll talk a bit about what is quantum cryptography, and in particular, what do I mean by untrusted devices? So basically explain the title of what I'm going to be talking about. Then Bell inequalities, which is the basic physical phenomenon that's going to power everything that I'll be doing here. Number 3 here is the basic mathematical tool that we develop to make this application possible. And then we'll talk about the two particular applications that I have in mind. So, first of all, what is quantum cryptography, basically? So, maybe I should apologize a bit. Like the set of slides was made essentially for a computer science audience, so you'll have to bear with me with things that might sound a bit basic to physicists. So basically, the starting point of quantum cryptography is that, well, in classical cryptography, we deal with bits. All information is encoded in bits. And of course, when we move to quantum mechanics, well, everything turns into qubits, so photon polarizations, electron spins, etc. And what happens when we do this is that all kinds of counterintuitive phenomena occur. And the phenomena that will be relevant here is the fact that, in particular, it's impossible to copy information. It's impossible to measure information without disturbing. And we get correlations that are impossible classically. Namely through entanglement, and we're going to be making use of all these facts here and apply them to do actual tasks. In particular, so the consequences on cryptography. Well, there's all kinds of consequences on cryptography, and I'll talk about the consequences on 2 possible tasks here. The first one is key distribution. So here the basic task is that we have 2 players. Usually in crypto we call them Alice and Bob, so they have standard names. And what they're trying to do is to establish a secret key. So basically a string of bits that is generated randomly. So it's supposed to be a fresh bit string, uncorrelated with anything else. And it's supposed to be they're supposed to get the same key, right? They'd like to use it as a password, for example, for something else, or to use it as a key to encrypt information later on, right? So that's the basic idea that's the basic task we'd like to do. And the difficulty is that we assume that those 2 players are not in the same place, right? So they're connected by, let's say, a fiber optics link or some communication link that is public, essentially, so that a spy could listen in on their communication, and which means that this is what makes the task difficult, right? Like they want the key to be secret from anything else. If there's a spy that can listen in on their communication, well, how can you do this? So to be able to do this, well, we're going to have to make use of all of these quantum phenomena. The fact that, in particular, a spy here would have to spy, they'd have to measure the communication if the link is quantum, which means that they'd have to disturb whatever is being transmitted, which means that in principle is detectable. So the whole game here is to create a protocol that enables them to catch a spy and figure out exactly how much information the spy could have acquired about the information that they sent, and then use this to be able to create a key that is secret at the end. The second application we'll be interested in is certified randomness. So here the idea is that we forget about the two players. We just want to create fresh randomness. So basically create a new bit string that is random, uncorrelated with anything else in the universe, and somehow be able to prove this from physical principles, right? So classically, it's essentially impossible to do, right? To be able to actually certify this, because wherever you get your information, there could be a copy of it in principle somewhere else, and there's no real formal way to prove this. We know that in quantum mechanics, there is intrinsic randomness, in the sense that you could take, for example, a state, I don't know, like let's say ket 0, you measure it in an incompatible basis, then you know that the measurement result is going to be random. So you could in principle use this to get fresh randomness like this that's uncorrelated with anything else. But now the difficulty is that there's no way to prove that your device actually does exactly what you're supposed to do, right? Like if you tell your device to measure in some basis, well, in reality, it's going to measure slightly off. To be able to certify the amount of randomness, you'd have to quantify by how much it's off and so on. And there's all kinds of issues that arise here. And here we'll see that there's a way to actually certify it from first principles, and in particular from this phenomenon here, the fact that we have correlations that are impossible classically, and this entails that these correlations has to come from this. There has to be some randomness involved here, and we'll see how this works. So what do we have in terms of, so we're going to have quantum protocols for both of these tasks. And basically the way most of these protocols work is that, so we have our two players, Alice and Bob. They're related by some communication links, which is quantum here. Let's say to make things concrete, we have a fiber optics link. And then here Alice has a laser to transmit, let's say, single photons, for example. Bob has some sort of measurement device at his end that he uses to read off the photons. And this link here is going to be, let's say, it's going to be public in general. Like the adversary is going to be able to read whatever is happening on this link, and in particular measure whatever happens on this on the fiber optics link. And here we have two problems that arise in general when we have protocols of this tasks. And the problem is that the devices are not perfect. And here we'll be interested in two sources of imperfection. So the first one is just the fact that the device is a real physical device. It's not built perfectly. So like I said before, if you try to, let's say your measurement device is supposed to measure in some basis, in general, it's going to be slightly off, and it's hard to quantify in this way. And the second source of imperfection comes a bit from the paranoia of cryptographers, and will be here we'll be considering devices that might come from a malicious manufacturer. So we won't even trust whoever is giving us the box. So what we'd like to do is just to buy a box, treat it like a box that we can't open, we can't really know what's inside. And it could even have been produced by a malicious manufacturer, and we still want to be able to use it in cryptographic tasks. Right? We want to be able to use it to generate fresh randomness in a way that wasn't pre-programmed by the manufacturer, right? Like we get a box, it's going to produce all kinds of values, it's going to communicate with another box built by the same manufacturer, and we want to be able to trust what comes out of it, even if we don't trust the manufacturer. So here's what the model will look like. Now we're going to forget about the inner workings of it. So we're going to forget that it's actually a fiber optics inside, and they're exchanging quantum information between them. what we're going to have here are just two boxes, right? Where Alice is going to have her box that we're not opening. We're not going to be interested in the particulars of what goes on because we don't even trust it. The same for Bob. They're going to be exchanging messages, but this is all we'll care about is the input-output behavior of those two boxes. And the only thing we'll really assume here is what we really have to assume, which is that the devices can't communicate with the eavesdropper. So Eve here is the standard the standard name of the adversary here. So here it's going to be the manufacturer, for example. We'll call Eve for eavesdropper. Essentially, it's a standard terminology in cryptography. So the model is that those devices can't communicate back to Eve because, of course, then there's no hope of doing anything, right? If the boxes can just tell after the protocol went on, just tell what the keys were, then there's no hope. But so we won't allow this, but we'll allow the manufacturer to pre-program these boxes arbitrarily. So, for example, if we have boxes that are supposed to generate fresh randomness, we will allow the boxes to, for example, have terabytes of data that's pre-programmed by the manufacturer, where the manufacturer has a copy, and then the box could try to, in principle, to just simulate what we're supposed to see in the real protocol while keeping a copy later. And now our job is going to be to devise protocols that can defeat this somehow. So what are the two tasks that we're interested in more detail? So the first one is device-independent randomness expansion. So here, what we want to do is what we'd like to do is to generate randomness. So we'd like to buy a box here that produces some bit string at the output, and we want the bit string to be uniform, independent from anything else in the universe. So we want it to just produce fresh randomness. And this is, well, as stated here, this is too good to be true. Like we won't be able to actually succeed at doing this. So we'll need to do two things to make this possible. The first one is that, well, it's not going to be randomness generation. We won't be able to start this from scratch. We're going to have to start with a little bit of randomness here. So we're going to have to start with a smaller bit string, random, and then use the box to make a much bigger bit string. So here we'll think of M as being much smaller than N here. Otherwise, of course, it doesn't make any sense, right? If we need randomness to make the same amount of randomness, it's not so interesting. So that's the first thing we'll have to do. The next thing that we'll have to do to make this possible is that, well, we're going to have to, it's not going to be possible with a single box, but it will be possible with two boxes. So here we're going to suppose that we actually have two boxes that are not allowed to communicate, or that are not allowed to communicate during the protocol. So one way to enforce this is to make them very far apart, and then make sure that the boxes have to respond in such a way that they don't have time to communicate with the other box while the protocol goes on. So, for example, by going fast enough that the response has to come before a signal at light speed would have time to reach the other box. So that's one way to enforce this. And we'll see that this makes it possible here. So here we're going to have our two boxes. We're going to have a little bit of randomness at both ends here that we're going to use to produce more randomness. And here the boxes are going to produce values A and B, and then we're going to be able to post-process rather A and B to get the randomness that we want out of it. So the idea behind randomness expansion is not new. So the problem was first considered by Roger Kolbeck in 2006. And then there's a number of results in that direction. The first one was by Stefano Pironio, Antonio Assin et al. In 2010. And here they had a security proof for a protocol that we'll see a bit later, or we'll see something very similar later. And it worked against classical adversaries. So basically the adversary could only keep classical information about the pre-programming of the devices. Right? So you could sell a box, and they could keep classical information about whatever they put into the box, but they couldn't keep, let's say, a quantum system that's entangled with it. Second result here by Vaziran and Vizik in 2012. Here they could prove security against quantum adversaries. So here again, an adversary that could keep quantum information about whatever was pre-programmed inside the boxes, but wasn't really tolerant to noise. So basically in the real protocol, as soon as there were as soon as you saw errors, then you were forced to abort. And then, so basically for any real world devices, what the protocol would do is that as soon as there's any noise, we get no key out, but it's secure. Right? If somehow you didn't get any answer, then you would get some key. So it showed that this was possible in principle, but in practice, there was really like this was a big handicap. And then Miller and Chsh in 2014, this did a little bit better. So it's a bit like Vazirani and Didzic, except that there was some tolerance to noise, but then the generation rate was poor. So basically we got the amount of randomness we got out of it was much less than what we would have expected from the protocol, and much less than, for example, this got. Second problem that we're interested in is device-independent key distribution. So now, again, we have 2 boxes here, and now the 2 boxes are in the hands of two separate players. Now we have Alice and Bob. So this is we have Alice here and Bob here, and they want to they want to use their boxes to produce a shared key. So we want Alice to have some random bit string here, k. So it's an n-bit string. We want Bob to have the same one. We want the bit string to be fresh and independent from anything else, and independent in particular from whatever the manufacturer could have, right? So the manufacturer could have pre-programmed those 2 boxes in such a way that they'd be able to figure out what the key is at the end. And this is what we want to prevent. Right? And again, this is the concept is not new. Again, Piranio and Nassin showed that this was possible against what's known as IID attacks. So IID here stands for independent and identically distributed. So what we mean by this is that these protocols, basically the way they work is that they work in rounds. Right? So we have n rounds of a very small sub-protocol. So for example, Alice is supposed to send 1 qubit to another one, or the box is supposed to produce 1 bit out. And then we do this n times. After the n times, then we have n, let's say n bits at Alice's side, n bits at Bob's side, and then we do some post-processing from that. And basically what an IID attack is that the attack happens, like the adversary does the same thing at every round of the protocol. Like the adversary attacks each round of the protocol in the same way all the time, which is of course a big limitation, right? An adversary is of course not limited by this. It's a completely artificial restriction on adversaries, but it makes the analysis much easier. So this is why they considered this. 2014, Vazirani and Didzic showed security against general attacks, so where we don't have this IID restriction. But here, the issue is that the key rate went to 0, so we get very little key out of the protocol. And again, we have no noise tolerance. So in real world, of course, we want to, if there are some errors, we want to be able to recover from it. So basically lower the key rate a bit, but not abort entirely. And then in 2014, Miller and Chsh had a noise tolerant protocol, but with a very low key rate again, like much less than what we would expect. So basically what we would expect essentially is that this IID restriction here, we expect it to be completely artificial, or we expect in the general case to be able to do just as well as in the IID case. And we'll see that this is what we'll achieve with the result I'm gonna present here. So why are these things possible at all? So the phenomenon that enables this is called the Bell inequalities. So also known sometimes as quantum non-locality. And here's the idea. So probably many of you have seen this. Again, this was meant for a computer science audience. So most of you have probably seen this. But here's the concept. So this was by John Bell back in '64. So here's the idea. So suppose that we have 2 players, Alice and Bob, that are separated, so far enough that they can't talk to each other while this game is going on. So yeah, this is basically we'll view this as some kind of game here with a referee in the middle and 2 players here that are trying to win the game despite the fact that they can't communicate. And here's how the game works. So the referee is going to come up with a question for Alice and a question for Bob. So the question for Alice is X, the question for Bob is Y. And then Alice is supposed to answer something. Bob is supposed to answer something. We'll see a concrete example a bit later. This is just the general setting. And then there's the referee determines a score for this. So the score depends on the questions asked and the answers that they get. And the idea is that for this to make sense, is that we have an inequality of the form that for any classical strategy, the expected score is going to be at most some value here of the game. And the limitation basically comes from the fact that this is supposed to go on too quickly for Alice and Bob to communicate. Like, so basically Bob has to answer B without knowing X in particular. And the same, Alice has to answer A without knowing the question asked to Bob. And then they need to produce something that's correlated despite this fact, right? So that's the limitation that goes on here. So here's a concrete example of this. This is called the CHSH game. And here the questions and answers are all bits. So it's all 0 or 1, each of them. So the referee produces a question for Alice, a question for Bob. So these are bits that are generated at random independently for Alice and Bob. And then Alice and Bob are supposed to respond with a bit. They each respond with a bit, and then they win if addition mod 2. So this is A plus B mod 2 here. So this is also a bit. Again, like I apologize for notation that was better in the computer science department. This is not a direct sum or anything like this. It's just the addition mod 2. So they win if the addition mod 2 of the two answers here is equal to the multiplication of the questions. And it's not too hard to show that the best classical strategy wins with probability at most 3/4. So basically, there are 4 possible pairs of questions that you can ask, and and you can show that whatever strategy you choose, then there's 4 possibilities. There's always one of them for which it doesn't work, regardless of what you do. So you end up with a winning probability of 3/4, regardless of the strategy that you follow. And of course, the interesting part here is that if you allow quantum, and by which I mean you allow Alice and Bob to share an entangled quantum state before the protocol begins, but once this is done during the protocol, they can't communicate. They can just measure the states that they have. Then they can do better. Right? And in particular, there's a quantum strategy for the CHSH game that we just saw. And the strategy is basically this, right? So at Alice, if the question that Alice gets is a 0, then Alice is going to measure. So this is a qubit, right? So this is phi here is just 1 over square root of 2 of cat 0, 0 plus cat 1, 1 here. So this is Alice has 1 qubit, Bob has 1 qubit, like fully entangled state. And so if Alice gets a 0 as her question, she's supposed to measure in this basis here. So this is just a basis that's like 0, 1, right? If she gets a 1, then she's supposed to measure in the diagonal basis. So diagonal being like 0 plus 1 and 0 minus 1. And then at Bob, the best strategy is to do the same thing, but slightly rotating. So instead of measuring the 0, 1 basis, you rotate by pi over 8, the 2 states. So you rotate in the Bloch sphere. And the same for 1, right? So you have something like this. And if you crank through the calculation, you'll see that the winning probability of the strategy is actually co-squared pi over 8, which works out to 85%, which is of course strictly greater than 3/4. So doing this is strictly better than any possible classical strategy. And the point here, the key feature of this is that for any quantum strategy that beats the classical bound, then there must be some randomness in the answers that come out here. And this is the phenomenon that we'll exploit here. If we can beat the classical bound, then whatever went on, like whatever strategy was used, there must be some randomness in what came out of it. And we're going to see that there's a way to quantify this. And then we're going to use this to combine it into cryptographic protocols. So yeah, so basically this is what I just said. So beating the classical bound means that A and B are partially random, even from Eve's point of view, right? So regardless of what Eve does here, so basically like this, you can imagine that we have our two boxes that are supposed to play CHSH, right? Like now we forget about the what was in the previous slide. So this was a particular strategy. Now we have two boxes that are supplied to us by a manufacturer that is supposed to play CHSH, but we have no idea of what goes on inside the boxes. So this is what's going on. And the point is that if those two boxes are able to play CHSH and beat the classical bound, then regardless of how those boxes were constructed, then there must be randomness that came out even from the point of view of the manufacturer. And that's what's going to enable us to do randomness expansion and key distribution with this stuff. So here I'm going to have to introduce some information theory here. So, like I said, there's some randomness in what came out of the boxes here. So to be able to harness that fact, we need to measure the amount of randomness that comes out. And one way to measure the amount of randomness is to use something called the entropy, which is denoted like this. So I'm not going to go into detail of how these things are defined, but you can think of it as, so this is the entropy of AB. So what came out, so the answers of the two boxes, given X, Y, E. So given the two questions that were asked to the boxes, and E here is going to be a classical system that Eve kept from the pre-programming. So you can think of it as when the two boxes were produced by the manufacturer kept some sort of quantum system at the factory, and then shipped out the two boxes. And now E is the quantum system that contains information about the pre-programming of the two boxes. And now this here is going to be the amount of randomness in the answers of the box from the point of view of someone who knows the two questions that were asked and whatever was in the pre-programming here. And what we need to be able to actually make the argument go through is to have a lower bound on this quantity in terms of what we see here. So the expected score of the game. So the higher the score, the higher this lower bound should be on the amount of randomness that is present in the two answers. And in fact, so there's a precise bound for this. So this comes from the 2009 paper by Pironio Asinbuna that I talked about a bit earlier, the previous work. So the bound actually looks like this, right? So this is turns out that we only use one of the two answers, like the other one we just throw away essentially. But we get a lower bound that looks like this. So we have a lower bound so this is 0.75, right? So it starts at the classical value of the game. If we're not beating the classical value of the game, we don't get anything out as expected. This here is the maximum quantum value. This is the best we can do with quantum mechanics, which is the strategy I showed a bit earlier for CHSH. And at that point, we actually get 1 bit of randomness out. So basically it says that the amount of randomness in A has to be exactly 1 bit of entropy. So A has to be completely random and independent from X, Y, E if we have an optimal strategy for CHSH. And in the middle, well, there's a curve that looks like this here. So I have the expression here. The details of this expression is not so important. All that matters is that, well, we have something, right? We have a lower bound for this thing. So now this gives us a lower bound for one instance of the CHSH game. And the entire challenge here is to be able to combine this, because we're gonna to be able to actually get a bit string out of it, and we need to replay CHSH multiple times, do all kinds of pre-processing on it, and then get a large bit string out. So we need to repeat this multiple times, and we need to somehow prove the fact that if we're doing this sequentially multiple times, then this bound is still true somehow. We can still use the bound for one copy of the game. There's no way to cheat by somehow combining the instances of the first instance of CHSH with the second one, or with the third one, and so on. So this is the difficulty here. So yeah, basically, more or less what I just said. So we know we can generate randomness in one isolated round of CHSH, the question is, how can we use this to construct a complete protocol? So we perform several rounds. Once we've performed several rounds, how do we do this? Right. So we have a bound that tells us how much randomness is produced by one round given the expected score of the game. Right. So and the expected score, of course, you can't get from a single game. A single game is just won or lost. You don't know the expected score of the strategy. Right? So then the thing you can do is to perform several rounds of CHSH. Then once you have several rounds of CHSH, there's some fraction of the games that you've won. And then you can look at the fraction of games that you won, and you use that as a substitute for the expected score of the game, and plug that into the bound. But of course, the problem is that if you do multiple rounds of CHSH, the adversary could do something else at every round of the game. Right? There's no reason to use the same strategy for every round. So it's not clear that the bound applies. Right? It's not clear that if I take the average of the score of each of these games, it corresponds to the expected score of a strategy used multiple times. There's no guarantee that the same strategy is used even twice among all of the rounds. And of course, the adversary can introduce correlations between the rounds. So we have to deal with this somehow. And of course, there's another problem here, which is we need some randomness to generate X and Y, right? So the questions that we're asking the box at every round are supposed to be random. But of course, the whole point here is to be able to produce randomness. How do we do this, right? Are we not burning the same amount of randomness as we're getting in, or as we're getting out? Well, the way we're going to solve this is by having test rounds and data rounds. So basically, in test rounds, we're actually going to play CHSH as usual. So this is where we're going to burn our randomness, and then we're going to have data rounds in which we're not going to play CHSH. Instead of that, what we're going to do is just fix the inputs X and Y to 0. So we're always going to ask 0 to the two players for those data rounds. And then the whole point is that if the adversary doesn't know which rounds are test rounds and which rounds are data rounds, then they're going to have to essentially hopefully play honestly for most of the games, which means playing honestly even in the data rounds when the questions are fixed. And then this is how we're going to get randomness out of it, right? We only burn a small amount of randomness to generate the test rounds, but then the boxes have to play honestly also in the data rounds, and there's going to be very few test rounds compared to the number of data rounds. And then by using that fact, we're going to be able to get more randomness out than we put in.
Fred, I have a question.
Yes.
It's important for this that, as you said, that the adversary does not know which are test and which are data rounds, of course.
Right.
But as soon as the adversary sees a 1 on one side or the other, he knows that. I mean, that half of the adversary, whenever 1 is given as input, it has to be a test round. So
right.
Some information about which is leaks. How do you deal with it?
Right. So the thing is, if one player gets let's say one player gets a 0, he has no way of knowing that the other player gets a 1, and if he gets a 0, plays honestly, and then whatever comes out has to be random anyway. That's the basic idea. So yeah, and I mean, if you look earlier, we even only look at one, like we only look at what comes out at Alice's side, right? So I mean, so basically, as soon as Alice gets a 0, the fact that Alice doesn't know that Bob got a 1 or not, essentially forces Alice to play honestly. And if Alice plays honestly, then whatever comes out has to be random. I mean, that's basically how this comes out.
That's fair enough. But if you allow me to answer my own question now, I thought somewhat more. It's because yes, someone can know that it's being given a test round when 1 is input, but
yes.
You have no advantage in trying to cheat in a test round. You only want to cheat on data rounds, and you never know that you are in a data round.
Right.
So being able to know that you are in test round doesn't give you anything because you don't want to cheat there anyways.
Right. Yeah. So I mean, what you would want to somehow to be able to cheat is to know that if you get a 0, you're in a data round, which you don't. Okay. So let me keep going. So So the next question is, we need to talk a bit about how to quantify randomness. So I talked a bit about this H quantity. So this is probably the best known measure of information, called the entropy. And it turns out that for our purposes, there's a second quantity that we need, called the smooth min entropy. So basically, this is a quantity that essentially quantifies the number of bits we're able to extract from a bit string. So so here's how it's defined essentially. So suppose that we have a system, so rho xe here, and x is going to be some classical system. So it's let's say some bit string that's partially secret, and E is going to be a quantum system that's partially correlated with X. So X contains some randomness, but not full randomness. And then the way we're going to quantify the amount of randomness in X from the point of view of someone who knows E is going to be in this way. So we're going to look at the probability of guessing X, the value of X, from measuring E. So we take the best measurement possible on E, apply it, and then use it to try to guess the value of X. And then the best guessing probability that we have is essentially going to determine the amount of bits that we can get out of it. So we're going to measure it as minus log of the minimum guessing probability by measuring E. And then there's this thing here where we're not going to look at the actual state here, but we're going to look at a state that's close in some sort of ball here with radius epsilon. Well, this is not so important. So basically, like if the guessing probability of X given E is something like 2 to the minus 1,000, we're going to say that there's 1,000 bits of smooth min entropy in it. And the point of this definition is that it, like I said, it characterizes the number of extractable bits in the following way. So suppose that we have our state here, rho xe, and we want to take X, process it in such a way that we get a bit string out of it that is smaller than X, but completely independent from E. So like completely decorrelated from E and uniform. So one way to do this is that there's something called an extractor here that's going to take X as input. We're going to choose a function at random among a family of functions. So an extractor is basically a family of functions that we choose at random, apply that function, and then we take the output of the function as it comes out. And it turns out that, so I'm not going to go into the details here, but it's possible to extract this many bits out of it. So the higher the min entropy, the larger the key we can produce with this process. So all that to say that our goal here is in constructing a protocol is to get a lower bound on this thing. Right? So we need to lower bound the smooth min entropy of whatever comes out of our boxes, and then apply this to get our final key. Right? So the main task is going to be to lower bound this thing. And what are we going to use to lower bound this thing is something called entropy accumulation. So this is the basic mathematical tool that we use here. And here's the motivation for this. Right? So our protocol is going to look like this. So it's going to be a multiple round protocol. So we're basically going to play our either CHSH or a data round. Like each of these is going to be like each of these blocks here is going to be either a data round or a test round. And it basically involves having our two boxes play, like being asked a question, answering a question, and so on. And the whole thing is going to look like this, right? So here we have our manufacturer here that produces the box in the first place, keeps some information about the pre-programming, and then we're going to use the two boxes in our protocol here. So one round of the protocol is going to be, well, we're going to let the two boxes, well, this is the boxes being programmed. Then we have our first round, ask the questions, the boxes produce the answers out of it. And here we collect all of the information. At the bottom, we collect all the information we put in the box and get out of the box. And then between the rounds, well, we could let the boxes communicate with each other, but not with Eve. And then we start again. Right? We just keep this going for n rounds. And then at the end, we get a bunch of random variables out. So we get all of the questions that we asked to x1, y1, x2, y2, and so on. We collect all of the answers that we get out of the box. And then we have something like this here. So we have n, 4 n bits that are in play here. And our goal is to bound the min entropy of the answers, the collected answers of everything, given the collected questions and whatever pre-program or whatever information the manufacturer kept about about whatever's inside the box. And what do we want the lower bound to look like? Well, we expect something like this here. So this is what we want essentially. So we want already the n, so n times like an average amount of randomness produced in each round. And in each round, what we expect is that it's going to be some function of the number of rounds won, right? Like if we look at our whole protocol, look at let's say we just look at the test rounds, look at the fraction of rounds that we won. This is going to be some sort of score, and we expect that the higher the score is, the higher the lower bound is going to be, right? So we expect the lower bound to be of that form. Here. And now the question is what is f, and so on. Right? So the first thing is to make this a little bit more abstract. So instead of having this whole complicated round, we're just going to have a sequential process like this. So each round is going to be abstracted away by a box here, m, that represents the two boxes doing their thing, the questions being asked, the answers, and so on. And here's what happens here. So each step of the process, at each step of the process, we're going to have two things here. So we're going to have O here. That's basically what we observe. Essentially, they're going to correspond to the answers produced by the box. S here is going to be something, some sort of side information that are produced by the process. Here it's going to be essentially the questions. And then we have E here, that's the same thing. And then C here, C is going to be some sort of check system that's going to represent essentially whether the round was won or lost. Right? So something we want to do statistics on. So here in the actual protocol, the statistics we do is that we look at the number of rounds that we win, so we do the statistics, and based on those statistics, we're going to have a lower bound that depends on that. And this is going to be the abstract version of all this. So we're going to have a few assumptions on all of these channels. So these are basically just normal quantum channels, so CPTP maps. First of all, these guys have to be finite dimensional. And the final bound is going to depend on the dimension. So we have to do this. C here is going to be classical. So it's a classical register that you can obtain by measuring these two. So OI, SI, without disturbing the state. So basically, OI, SI contains a copy of CI. And then there's there's a technical condition here in that, so basically SI here has to be generated from S1 to I-1 and E alone, without reference to the previous one here. So basically, what it corresponds to in the protocol is that it can't be the case that, for example, the future questions here contain information about past answers, because then that would destroy future rounds would destroy the bound that you created in previous rounds. And here in this protocol, it's basically done by construction, because the questions here are just generated fresh at random, so they can't depend on previous ones, but we need to include this condition in the abstract version to prevent this from happening. So yeah, basically what it says is that future S's here tell us nothing about the previous O's. So the future side information doesn't spill the beans about previous observations. And then, so we want our bound to depend on the statistics observed on C1 to Cn. To make this a bit more precise, well, we're going to define frec C1 to n here, so which is going to be the empirical distribution on C1 to Cn. And what I mean by this is that, like, let's say C1 to Cn are bits. Let's say it's a bit string like this. Then the empirical distribution is just the fraction of positions that are ones versus the fraction of positions that are zero, right? So this is like a probability distribution on one copy of CI that depends, that's basically the empirical distribution of what you see over the whole thing. And now, what do we want? Well, we want a bound of this form. So we want a bound on O1 to n, given the side information S1 to Sn, and given Eve's side information. And we want it to be in terms of the number of rounds that we do. And it should be a function of the statistics that we observe on C1 to Cn. And here more precisely, just to essentially reformulate here. So we want a bound that looks like this. So the min entropy of these things, given that the frequency that we see on C1 to Cn is equal to some value q, right? Because so this is what we observe at the end, and we want a bound that is conditioned on what we see. And we want this to be at least n times, so this some function here of the statistics that we observe. And what we'll actually do is to generalize it to a set of frequencies that we can see, right? So basically, as long as, so we're going to have a bound that applies as long as the empirical distribution that we see is in some set here of acceptable distributions. To go back to our CHS example, it means that as long as the number of rounds that we win is at least some lower bound, then we're happy. Right? Omega is going to be like win some number of of games or more. And then it's going to be at the lower bound is going to be at least n times the worst case over omega. So then this f here, we're calling it the trade-off function in the paper, because it's essentially encodes a trade-off between the amount of randomness produced and the distribution on the CIs, and it's defined this way. So it's some lower bound on the amount of, and this time here is the regular entropy of one. So we look at one round here, and we look at the worst case amount of entropy in OI given SI and this R prime here. So we forget about the fact that we have n round. We focus on a single round, look at the amount of entropy that's produced in OI given this SI and whatever comes up here. Here we take the worst case input that we can give the process. And then we look at the amount that's produced here. So that's basically how it is. And basically, this essentially works out to a correspondence between the probability distribution on one copy versus the empirical distribution on n systems. So it's not so trivial to prove that this passage from the distribution to empirical distribution actually works. But this is basically the heart of the argument. And so what the theorem says is that once we define all of this, then we do have a bound of this form. And so the bound looks like this. So it's exactly the sort of thing we're interested in lower bounding. And what the lower bound is n times t. T is exactly this infimum of the worst case of the trade-off function over omega minus, and then there's some lower order term here. That's also important. So it scales as square root of n rather than n. And then the coefficient in front just depends on a few things. Like it depends on how sensitive the trade-off function is to its input. Like if the amount of randomness varies enormously, if you shift the statistics a bit, then this term is worse. Depends on this smoothing parameter epsilon. It depends on the probability of being in omega. Basically, if you assume that for example, if the adversary could be extremely lucky, right? Like you could, for example, have an adversary that's cheating at every round and then winning every single round. It's theoretically possible. And then you would, of course, accept this at the end. But the point is that it's extremely unlikely. So if you assume that that what you see was extremely unlikely, then you essentially, like, your bound cannot be good, basically, because then the adversary could be extremely lucky and just being able to win all the games while cheating. Right? So basically, you need to assume that the adversary is not incredibly lucky. So what it means in practice is that you'll just assume that that what you see had probability at least some number you're comfortable with. I don't know, like let's say 2 to the minus, I don't know, 50 or something. Let's say you're comfortable that the adversary was not that lucky, and then given this, then you have a bound. And then it depends on how big each of these OIs is. So that's the dimension of OI. And then, so how do we use this to do randomness expansion? So to do randomness expansion, so here this is the problem where we're just interested in generating random strings. Then for every round, well, we're going to choose questions to xi and yi, get the outputs here to all of them, set ci here to be the score, so whether we won or lost that game. So the score is here is just 1 or 0, and then we abort if the sum here of the ci, so this is basically the number of games we won. If this is too low, then we abort, and this is like the expected number of games that the number of games we expect to see minus some tolerance parameter, and if it's too low, then we just abort. So that basically means that we're outside this omega that I talked about, and then we get our lower bound, the entropy accumulation, and then we can use this to get the key out using this extractor trick I talked about a bit earlier. And of course, the trade-off function is exactly the curve I showed you earlier. So this comes again from that paper. This is the analysis of one round of CHSH. This we can just use it verbatim as our trade-off function. And essentially, what it boils down to is that in this paper they analyze a protocol where the adversary is limited to doing the same thing at every round. And here we show that lifting this restriction to a general adversary that can do anything over the full thing basically comes for free. Like we don't pay any price for it. We get the same amount of key out. And here's so we have some curves here of what this works out in practice. So if we have concrete values of n here, so the number of CHSH, at least if we plug this into our bound, then we see what happens, right? So if we have, let's say, 10 to the 8 positions here, then we get pretty close to the infinite rate that we get. So IID asymptotic rate means like with n going to infinity, what do we get? And of course, the shorter the block length, the worse things get. And then there was some subsequent work as well. So Knil, Zhang, and Fu here they managed to get a slightly smaller block rates before we get non-trivial key rates. And it comes at the price of being a bit more difficult to compute. So it's a more monolithic proof, so to speak. And then second application is device-independent key distribution. And again, so now Alice and Bob are in separate labs. We have to do some error correction as well. I don't want to talk about this since I'm already out of time. And then, so part of the one problem that we have to solve when doing key distribution is that, well, at the end, we want Alice and Bob to have the same key. And when playing CHSH, this doesn't happen. Right? Like even the optimal strategy, Alice and Bob in general don't have the exact same answers out. So how do we fix this? Well, we're going to modify the game a bit. So Bob, instead of having 2 inputs, he's going to have 3 inputs. If the input is, so the 3 inputs are 0, 1, or this bot, /bot in LaTeX here. So if the input is this bot here, so he's just going to measure the same basis in the same basis as Alice in base 0. So whenever Alice gets 0 and Bob gets bot, they're supposed to get the same value. And then in the test rounds, then Bob is going to get either 0 or 1, and then they're supposed to play CHSH normally. So of course this means that Bob knows exactly when there's a test round, but Alice doesn't, and that's enough. And then here's the sort of thing that so if we work out the numerics here, so I think Q here is the error rate, like in a realistic scenario. Like if you get, let's say, 0.5% error rate, then we still get pretty good key rates. So like we get this is the key rate as a function of how big the block sizes are, and then we get different curves for the amount of noise that we have. If you see, like if you see at, let's say 5%, things get significantly worse, and so on. So conclusion and open problems. So two big open problems. The first one is blind randomness expansion. So here you could imagine that you could make one of the two devices completely controlled by the adversary, meaning that that device is even allowed to talk back to the adversary during the protocol, but not the other one. Because if both of them can do it, it's hopeless. We know that it's possible in principle. So there's a paper by Miller and Chsh, 2007, that show that it's possible, but they don't get particularly good rate. The question is whether we can use these techniques here to get good rates. And to do this, essentially, the challenge is that we have to let Eve's system to evolve during the process. Second one is a parallel version of these tasks, where the questions are asked in parallel. So basically, in this version, each round is done sequentially. Like the questions for a round are asked after the answers have been received for the previous round, and so on. Can we do this in parallel? Like, can we ask all the questions in parallel, get all the answers in parallel, and so on? So we know that it's possible in principle. Can we get good rates? So I think I'll end here since I'm completely out of time. So I'll just drop the papers here. So yeah, there's a short version in Nature Communications, and then the full versions here. Thank you.
Merci Frédéric pour le beau séminaire. Donc, c'est ouvert aux questions. Que j'encourage, I encourage the students also to feel free to ask questions.
I think Rufus raised his hand.
Oh, maybe he was clapping.
Oh, okay.
Because I have questions, but if anyone else wants to intervene first, feel free.
Yep.
Maybe I'll go. I don't see any resistance. Perfect. So Frédéric, maybe I'll ask in English just for everyone. Can you show again this accumulation theorem for the entropy?
Yes.
So I had a few questions about it. So when you define the set of states that's near your given state, and the epsilon appears there, right, to define your ball. Yes. What measure do you use? Is that important, or?
The answer is it's not very important. So the measure we use usually is it's called the purified distance. So it's essentially comes from it's like a distance measure that's defined from the fidelity. Not sure I have I'll probably mess up if I write it directly. And
it's recorded, so don't.
Yeah. I mean, but I mean, so the point is, the reason we use this is for considerations that are not really related to this. Like there's also something called the max entropy, and just to have a nice duality relation between the min and the max entropy. Like you have something called, so you'd have h min of A given B, which is equal to minus h max epsilon of A given C, where like rho ABC is pure. To get this relationship, then you need to use this particular distance measure. But I mean, for this year, you could use something else, and it wouldn't change anything in particular. Like in particular, you could use the trace distance, and often we just convert between them, and like in one direction there's a square root that appears, and yeah, so it's like it can't be zero. So we need to use some distance measure, but the precise distance measure we use doesn't really change much.
So does it change the the two terms on the right-hand side, the lower bound, or?
Well, I mean, it's going to change
like so the V, is the V sensitive to?
No, not very. Like the V is like, it depends something like log minus log of epsilon, something like this, right? So it's something like this. If you switch the distance measure, then you might get a square in there. Then you get a factor of 2 here. But this is supposed to be a small term anyway, right? So it's basically the worst thing that happens here.
But I gather, so you say V is minus or log of 1 over epsilon, so V is always positive, right? That's something that...
Yes. Yeah. So I mean, epsilon is always going to be less than 1, basically. So
of course. But you're saying V is actually equal to log of 1 over epsilon.
No. So it depends on all these things. So it's like the dependence on epsilon looks like this.
But is V known, or is
maybe I have it in the extras here later, or not.
But it has to be positive. And do you have like some simpler understanding for why it's square root and why it's the V is positive?
Well, not really. I mean, I don't think this is optimal either, right? Like this is basically what we managed to prove. I don't really have a good sense of what this term really should be somehow. Because I mean, the reason why we needed to use this epsilon is so I mean, if we take epsilon to be 0 here, like the min entropy is actually very, very sensitive to the state that we computed on. So to remove that sensitivity, then we allow to compute it on something nearby, because the reason is that if we imagine that the state we actually have is actually something slightly off from it, then we know that whatever we do with this state, if it's sufficiently close, then we'll never be able to tell the difference no matter what we do. So it can't change the security by that much, but it could change the min entropy by a lot. Right? So this is why we need it. But the exact distance measure that we use is not really gonna matter too much in the end, because as soon as you allow a little bit of tolerance, then you get rid of this sensitivity problem of the min entropy.
Got it. Okay, well, thanks. And then we have a question by Philippe Lamontagne. So Philippe, so I feel bad, but I can ask another question in case Philippe finds a solution. Maybe his channel is being corrupted by Eve. Oh, okay, so yeah, there is a question. So Frédéric, do you want to read it and answer it?
Yes. So here's the question. So what do you mean by parallel repetition in the open question? Since you only have 2 devices, you can only query them sequentially. So it's not like we query one device then the other device. The idea is that we just have, so I mean that in parallel, I mean doing all of these rounds here in parallel. I should have, yeah. So doing all of these rounds in parallel. So basically, in what I presented here, for example, x2 has to be asked after A1 is produced. So this is the sequential restriction here. And here the question is whether we can just ask x1 to xn all at once to the first box, y1 to yn all at once to the second box, and then have them answer like together.
Okay, good. Do we have other questions before I ask one more question? Okay, good. Well, my question was about experiments. I don't know. I was curious whether this protocol actually was tested, or is it even, do you think it's realistic, or there are some big shortcomings that make it not so enticing for the real world?
I mean,
do you have any comments on that?
So I mean, it's very close to being practical, let's say. Like I don't really have references at the moment, but so I think a few years ago we were just at the limit where we could see something, like we're something like, I don't know, here or something like this, right? So what we had was, so I think so I'm not sure how good it is now, but let's say a few years back, I think we basically had experiments where it was extremely slow, in the sense that we could only do one round every, I don't know how quickly, but then if we waited long enough, then we were able to actually run this, right? So it was just at the limit where it was possible somehow. And I don't know how much. I haven't really seen much since then. I'm hoping it got better, but I'm not sure. So I'm not an experimentalist, so
do you have a patent on this? Because maybe you'll be rich someday if.
Oh, no, I don't have a patent on this thing. Maybe it's a big mistake and I'll regret it. But...
That's right. You could retire early.
Yes.
But okay. Well, we'll follow the developments.
Yeah.
Maybe you can let me know if.
Yeah. Oh yeah. So someone put the reference in the chat also of one of these. So there was that Knil, Zhang, and Fu result. So they had an experimental component to it, I think.
Okay, it's from 2018.
Yes.
I guess we can start there and see those results and the follow-ups.
Yes.
Cool. Well, I think you've been tortured enough with questions. Donc, merci encore, Frédéric, d'avoir pris le temps.
Merci beaucoup pour l'invitation.
Puis, au plaisir, en personne, j'espère.
J'espère bien.
Take care, Frédéric, and everyone else, and we'll see you hopefully next week. Okay. Merci.